Okay, now let's talk a little bit about configuring the single area OSPF for version 2, which is our IPv4. As we talk through this, we're going to keep in mind this particular topology that you see here on the screen. We've got our 3 routers, and then we have our internet connection. We also have a loopback. The loopback is going to be our WAN connection to the internet. OSPF version 2 was introduced in '91, and it is a linked state routing protocol. And it was designed as an alternative to another IPv4 routing protocol, and that was RIP. So keep in mind this topology that we're going to work with as we go through and discuss single area OSPF. With the topology that we're showing here on our 3 routers, we're going to have OSPF version 2 enabled, and the command that we'll use is the router OSPF and then the process ID, and that's done in global configuration mode. Your process ID is administrator assigned, and it can be anywhere between 1 and 65,535, so you have a large range of IDs that you could possibly use. The ID value is locally significant, so it's locally significant to that router, not to the other routers involved. And that means that you don't have to match up your router IDs when you're establishing adjacencies with your neighbor routers that you're using. So the command that you use is just simply router OSPF, and then you give it the number that you're wanting to use. Once you've done that, in order to get into the next set of commands, you can always hit the question mark to give yourself all the additional commands that you can use with router OSPF. Remember, your question mark is kind of like your help. So when you practice that, you will see that the list is much more extensive than the one that's showing here. This one is just giving you an idea of what can be out there. And make sure you practice config in here. It's a great place to start and to practice before you actually hit a live router. Now, every router requires a router ID, like we said, to participate in an OSPF domain. And that router ID can be defined either by you, the administrator, or it can be automatically assigned by your router. And the router ID is used by OSPF enabled routers. Okay? It's not used by other routers, it's used by the OSPF enabled router. It is either going to uniquely identify the router, and it's going to participate in the election of the DR. When it's used to uniquely identify the router ID is used by other routers to uniquely identify each router within the OSPF domain and all packets that originate from them. Now, to participate in the election of the DR, when you have a multi-access LAN environment, the election of the DR occurs during initial establishment of the OSPF network, and when that OSPF link becomes active, your routing device that's configured with the highest priority is elected as the DR unless you have another one assigned with a higher priority, then that one becomes the DR. Also, the second highest priority is going to become your BDR. Now, with our Cisco devices, the router ID, when it's automatically generated, is done so by one of 3 ways. It can either be done by the router ID is explicitly configured using OSPF router ID, router configuration mode command, and the RID value is any 32-bit value expressed as an IPv4 address. And this is a recommended method for assigning a router ID, so keep that in mind, it's recommended. The other option is if the router ID is not explicitly configured, the router chooses the highest IP address of any of configured loopback interfaces, so you have to already have your loopbacks configured. And this is the next best alternative to assigning your router ID. And then finally, if there are no loopback interfaces configured, then your router chooses the highest active IPv4 address of the physical interfaces. Okay, so it's looking for the ones of the interfaces. And this is the least recommended method because it makes it more difficult for administrators to distinguish between specific routers. Okay, so keep that in mind. Your preferred method is for it to be explicitly configured using the OSPF router ID RID. Then the next is for loopback, and then the least favorable is for it to decide the highest level of a different physical interface because you're not using your explicit or your loopback. Now, if you chose to use the highest IP address for the router ID, then the interface does not need to be part of OSPF enabled. It just means that the interface address does not need to be included in one of the OSPF network commands for the router to use the IP address as the router ID, and the only requirements is that the interface is active and isn't up, so it's had the no shutdown done on it. One of the reasons why it doesn't show up in your routing table is because your router ID may look like an IP address, but it is not routable, and that's why it's not showing up in a routing table unless the OSPF routing process chooses an interface, either the physical or the loopback, that's appropriately defined by your network command. So keep that in mind. So let's look at how we're going to actually go in and manually configure the router ID, RID router configuration mode. Here in this example, you'll see that in figure 1 that router 1 is configured with router ID 1.1.1.1, router 2 is 2.2.2.2, and 3 is 3.3.3.3. And if we were going to use this same convention, then router 4 would be 4.4.4, and so on. So in figure 2, the router ID 1.1.1 is assigned to router 1, and the way in which we do this is we do router OSPF10, because we had to give it its ID. Now we're doing router ID 1.1.1.1, and you'll see how it looks like an IPv4 address, but it's not. It's the router's ID. And then you can see that you have it set up correctly. You do the show IP protocols, and then you'll see that it says router ID 1.1.1. Now, if you have a neighboring router with the same router ID number, it's going to give you an error and tells you that it's detected a router with duplicate router ID. You just simply change your router's ID number so that they don't have the same router IDs. Now, there are times when you need to go in and change your router ID. This particular one that it's showing has a router ID of 192.168.10.5, and they want it changed to 1.1.1.1. So if you were to go in and tell it router OSPF10 and give it the router ID of 1.1.1.1, it's going to tell you that you need to reload or use clear IP OSPF process command for this to take effect, because it doesn't let you just rename it. You're going to have to clear out the old one in order for the new one to take place. So in order to do that, you would do clear IP OSPF process, and it's going to clear out, just as it said here, it's going to clear everything out in order for this to take effect. You'll also notice that once you did the clear, that what it's done is it's taken the interfaces and bringing them down in order to clear things out, and then it's going to bring them back up. You can also assign your router ID. Can be assigned using a loopback interface, because remember, your loopback interface isn't an actual interface. The IPv4 address of your loopback interface should be configured using the 32-bit subnet mask. So that's the ones with all the bits turned on. So when you do interface loopback 0 in this instance, and then we do IP address 1.1.1.1, make sure you put your subnet mask on there of 255.255.255.255. That's how this one works. And some of the older versions of the iOS do not recognize the router ID command, and so the best way to handle that is to set the router ID on those routers is by using the loopback interface. So that's one of the things you need to have in your arsenal of tools as a network administrator is to know that if you're running something on an old iOS that doesn't take the router IDs, that this is one way around it, is by assigning your loopback interface. Next, let's talk a little bit about the network command. It determines which interfaces participate in the routing process of the OSPF area. So what part of that network is going to be used. Any interfaces on a router that match the network address in the network command are enabled to send and receive OSPF packets. So the network or your subnet address for the interface is included in your OSPF routing updates. So the basic command syntax is network. You give your network address, your wildcard mask, then area, and your area ID. And then we have to determine what our wildcard mask is. Now the area ID syntax refers to the OSPF area. So remember, if we gave it OSPF 10, then it would be 10. When configuring your single area OSPF, the network command must be configured with the same area ID value on all routers. Although any area ID can be used, it's a good practice to use an area ID of 0 when you're using a single area OSPF. That way you're not having to keep up with all of them. Just makes your life easier. And this convention makes it easier if the network is later altered to support a multi-area OSPF. You don't have to remember what have I used, what can I use. Start out with 0. So here we'll notice that we've got our routers. This is on 172.16.30. This is on 172.16.20. Here we've got 172.16.10. This is on 192. So is this one and this one. So they're on different networks than these three guys. You'll also notice that this guy here is a 30-bit. These two are 24 bits. Okay, so we're going to take a look at their subnet mask to come up with their wildcard mask. OSPF is classless by design, and the wildcard mask is always required. Because it is classless, you have to determine what's still available. When identifying the interface that are participating in a router process, your wildcard mask is typically the inverse of your subnet mask configured on the interface. So, the wildcard mask is a string of 32 binary. It's used by the router to determine which bits of the address to examine for a match in the subnet mask. Now, in your subnet mask, you have your ones turned on. To create your wildcard mask, you're going to flip it, and you're going to turn your ones to zeros and your zeros to 1. The wildcard mask bit 0 matches the corresponding bit value in the address, and the 1 ignores the corresponding bit value in the address. Okay, so if it's a 0, it matches to what's there. If it's a 1, it doesn't even look at it, basically. The easiest method for calculating the wildcard mask is to subtract the network subnet mask from 255.255.255.255, because that's with all your bits turned on. So the example here, we have them all turned on. This is a /24. So we subtract our /24 from our 32, and we have 000.000.000.255. Now if we had a /26, here your last octet would be 192, and when you subtract that, your last octet is a 63. There are several ways to determine which interface is going to be used when you're creating and configuring your single area OSPF. Here in this instance on figure 1, it displays what's the required commands to determine which interface on router 1 participates in OSPF version 2 routing process for an area. You'll notice that we use the wildcard mask to identify the respective interfaces based on their network addresses. So here we have OSPF 10, and it's going to go to network 172.16.1.0. with the wildcard mask of 0.0.0.255. It's going to area 0 as we mentioned earlier. Then we have network 172.16.3.0 and it's going 0.0.0.0.3. And then we have network 192.168.10.4 and that's using the wildcard mask of 0.0.0.3. If you look at this topology here, it's using this network, the 172.16.3 and the 192.168.10. Another option is that we can give the network ID and we can, for that particular interface, and we can give the quad 0. And we must also include the area and the area number. Okay. The advantage of specifying the interface is that your wildcard mask calculation is not necessary because you're using the quad 0. And OSPF2 uses the interface address and the subnet mask to determine the network to advertise. Now some of your iOS versions will allow the subnet mask to be entered instead of the wildcard mask. Some will not. So you need to make sure that you know which iOS that you're using. Now, by default, OSPF messages are forwarded out all OSPF enabled interfaces. Okay, and if we'll look at the topology here, that includes the gigabit ports on these routers who aren't going to any other router. They're going out to the LAN. And having these messages sent out where they're not needed affects your network in several ways. You have inefficient use of your bandwidth. You have inefficient use of your resources, and you also have an increased security risk. One of the security risks is that you're advertising updates on a broadcast network is a security risk, and OSPF messages can be intercepted with packet sniffers. So you really don't want your messages going out of interfaces that don't need to receive them. Now the way that we're going to stop this from happening is when you're in your router OSPF and your ID, you're going to give the command passive interface and then the interface that you do not want the messages to go out on. So in this instance, we have router OSPF10, we have passive interface, the gigabit Ethernet 00. That way it takes that interface and doesn't allow your messages to travel across through them. Both OSPF version 2 and version 3 support this method. Once you've put your interfaces that you need into the passive interface state, you can do show IP protocols to look and make sure that your passive interfaces are set up correctly. Make sure you didn't assign the wrong one, or make sure you assigned any at all, that you've not forgotten something. Alright, now let's talk a little bit about cost values with OSPF. You'll remember that our routing protocols use a metric to determine the best path that our packet is going to use to go across our network. And that metric gives identification of the overhead that's required to send a packet across a certain interface. Remember, we've looked at those numbers before. OSPF uses a cost as a metric. A lower cost indicates a better path than a higher cost. Okay, so it's going to add it up and determine which is the best way to go. So the cost of the interface is inversely proportional to the bandwidth of the interface. So a higher bandwidth indicates a lower cost because it goes faster. More overhead and time delays equal a higher cost. Okay, so you'll notice here in our diagram we've got an interface that's a 10 gigabit. The reference bandwidth is 100 million and the default bandwidth is 10 billion. You divide the 100 million by the 10 billion, you get a cost of 1. Okay, and you'll notice as we keep coming down this chart that our Ethernet is a cost of 10, a serial at 1.544 megabits per second is 64, and then our other serials get to an even higher cost. The default reference bandwidth is 10 to the 8th, So the formula is cost is equal to the 100 million divided by the interface bandwidth. Okay, so that's how you're going to determine it. I'm not going to make you do this without a calculator, so don't freak out on me. So now let's look at our topology again. So if our cost of the OSPF route is the accumulated value from one router to the destination network, not necessarily to the next router, but to the destination network. So here in this one, in figure 1, the cost to reach R2 LAN from R1, we've got a serial link from R1 to R2, that's a cost of 64. Then we have a gigabit Ethernet link on R2 to get to that network, which is 1. So 64 plus 1 is a cost of 65. Okay, do you see how we got that? This has a cost here of 64. It is a serial interface at 1544. This is a gigabit interface. Gigabits have a cost of 1. This particular serial here has a cost of 64. This particular cost here is the 64K. If we go back, our 64K has a cost of 1562. Okay, and then this one's a 1024. So it has a cost of 781. Okay, we want our packets to go with the cost metrics that's the lowest number. Okay, so I can do show IP route, and on this particular one I've told it to include the 172.16.2.0, oops, sorry about that, which is this network. Okay, and you'll see here it has its cost listed. It also tells you that the metric is 65 and that the route metric is 65 when I do a show IP route to that network. So we get a lot of information from that. We also can look at auto cost reference for our bandwidth. And the OSPF is going to use a reference bandwidth of 100 megabits for any links that are equal to or faster than the fast Ethernet connection. So your 10 gig, your gig, your fast Ethernet, your 10 gig, your gigabit are all at a cost of 1. Okay, then your fast Ethernet is the 1 billion divided by 100 million. That gives you a cost of 10. Okay. While the calculation works for fast Ethernet interfaces, it's problematic for links that are faster than 100 meg because the OSPF metric only uses integers as its final cost of a link. Okay, so if something less than an integer is calculated, it's just going to round it up to 1. That's why your 10 gig and your gig are all at 1. So we're going to assist our OSPF to make a better choice by making the correct path determination, and we're going to do that instead of going at a reference bandwidth of 1,000. We're going to bump it up to 10,000. Okay, then we're going to have our separation here between our 10 gigabit port and our gigabit port. Okay, so that's going to help us in our cost a little bit more. Now, all your interfaces have a default bandwidth value assigned to them, just as the reference bandwidth and the interface bandwidth values do not actually affect the speed or your capacity of your link. It just is part of the cost metric that's involved. So it's important that the bandwidth value reflect the actual speed of the link so that the routing table has accurate best path information. Although our bandwidth values of Ethernet interfaces usually match the link speed, some other interfaces may not. An instance there could be an actual speed of a serial interface is often different than the default bandwidth. And with our Cisco routers, the default bandwidth on most serial interfaces is set to 1.55. Some of our older serial interfaces by default are 128. You would use your show interface command to determine the interface bandwidth. You can see that here where we've done show interface 0000. You'll see that the bandwidth of that particular interface is 1544. And if I do show IP OSPF interface on the serial interface, I'll see its cost. So there's different ways that I can look at my interfaces to get the information that I need to see what cost is being used, to see what speed they're going at. So all these show commands are important in when you're determining the speed of your network and how your packets are going to travel. Now we may want to change the bandwidth of our interfaces. This doesn't actually change the bandwidth, it just changes the metric when it's configured that way. To adjust the interface bandwidth, you're going to use bandwidth and then you give it a number that's in kilobits. Okay, so keep in mind this doesn't actually change the speed of that interface, it changes the metric used for that interface. You can also once you've set the bandwidth to what you're wanting it to do to change your metric, if you need to go back and set it back to the default, you just go back in and tell it no bandwidth, and this will take that command and turn it off. Now, there is an alternative to setting the default interface bandwidth. You can do the cost manually configured for that interface by doing IP OSPF cost and then the value for that interface. One of the advantages of configuring the cost over setting the interface bandwidth is that your router's not having to take the time to calculate and come up with the cost because you've already given it its cost. Both the bandwidth interface command and the IP OSPF cost interface command, they end up doing the same thing, which is to provide an accurate value for your OSPF. So they both work the same, it's just different ways to get there. Now that you've taken your time to set up your OSPFs in your single area, you're going to want to make sure that your router has neighbors, and you're going to want to make sure that it can see its neighbors. So you're going to do the show IP OSPF neighbor command, and when you do this, you'll see your neighbor's ID, you'll see the state that they're in. So you also see what's called PRI, that's the OSPF priority of the interface. This value is used in the DR and the BDR. You have the state. In this case, in the instructions on the image here is showing you they're both at full. That means that the router and its neighbors have identical OSPF LSDBs. On multi-access networks, such as an Ethernet, two routers that are adjacent may have their states displayed as two-way, and the dash indicates that no DR or BDR is required because of the network type. Okay. Then you have your dead time. That's the amount of time remaining that the router waits to receive an OSPF hello packet from the neighbor before declaring the neighbors down. And this value is reset when the interface receives a hello packet. Okay, so the address is the IP4 address of the neighbor's interface to which the router is directly connected, and then you see which interface is being used. Some of the other things that you can look at with the show IP OSPF neighbor is you may have two routers may not form an adjacency. And some of the things that you need to look at there is the subnet masks do not match, causing the routers to be on separate networks. The OSPF hello or dead timers do not match. The OSPF network types do not match. And there's a missing or incorrect OSPF network command. So if you know that you should have an OSPF neighbor to a particular router and you're not seeing it, you need to go back and look and make sure that you have set everything up. Make sure you've not fat fingered something. Make sure you didn't put them on different subnets. That's easy to do, especially if you fat finger something. So those are some of the things that you need to look at while you're troubleshooting this. The quickest way to verify your OSPF interfaces is to do the show IP OSPF interface brief. Similar to our show IP interface brief, but if you do the show IP OSPF interface brief, it's going to show you the OSPF ones that OSPF is set up on.